In the previous slides, we have talked about how to bind logical address with a physical address. Now let's look at what the logical address and the physical address really are. So logical address is the address generated by CPU. So sometimes it is referred as a virtual address. Logical address space is a set of logical addresses generated by a program. On the other hand, the physical address is the address seen by main memory unit hardware. So physical address space is a set of physical addresses generated by the program. So actually, the major things we deal with in memory management is how to efficiently and correctly bind logical address space to a separate physical address space. Remember in the last slide, so we have talked about the three addressing binding schemes, which are compile time binding, load time binding, and execution time binding. For the compile time binding, after the compilation, the code will be changed to absolute code. So when the absolute code has been loaded into the main memory, it will be loaded into the specific location of the main memory because their address are already absolute addresses. So the addresses in the code are the same as the addresses on the main memory. So therefore, the logical and the physical address are the same in compile time binding scheme. Similarly, for load time binding, even though after compilation, the addresses of the code are relocatable addresses, but after loading, the relocatable addresses of the code will be changed to absolute addresses and load onto the main memory. So therefore, logical and physical addresses are the same in load time binding scheme. However, for execution time binding is different. So before the code get executed on the CPU, so their addresses are logical addresses, which means that so when the code has been loaded onto the main memory, they are still with logical addresses. Until they are executed on the CPU, their addresses will be dynamically changed to physical addresses. So therefore, the logical and the physical addresses are different in execution time binding scheme. Now let's look at the hardware that help us map virtual address to physical address. The hardware is called the Memory Management Unit, or shortened as MMU. With the help of MMU, the user program only need to deal with the logical addresses and never sees or be aware of the real physical addresses. So when the program is executed on the CPU, and when the CPU needs to access the main memory to get some data or other part of the program, the CPU only needs to pass the logical address to the MMU. By execution time binding scheme, the MMU will dynamically translate the logical address into physical address. Now let's look at dynamic relocation with execution time binding. Here we just introduce a simple mechanism which uses a relocation register. For relocation register, actually it is just the base register. So we gave it a different name because we use it for a different purpose. The idea is quite simple as shown in the figure. So when the CPU wants to access some location on the main memory to get some data or some instructions, the CPU only needs to provide a logical address and send it to MMU. Then MMU will add the value of this logical address with the value of a relocation register together to get the physical address. Then send this address to main memory and access that location to get the content stored there. So here you can see that the relocation register is only used for dynamic relocation, although it is the same as base register, but it is never used to check the validation of the memory address. In order to check the validation of the memory address sent from the CPU, so we need both base and limit registers together to achieve this goal. So when we talk about the relocation register, it is only used for dynamic relocation purpose. So here, we only introduce this very simple mechanism for the dynamic relocation. Later, we will learn more possible methods that address the dynamic relocation problem. Now, let's look at dynamic loading. So when using dynamic loading, routine is not loaded until it is called. So for doing that, it can achieve better memory space utilization because the unused routine is never loaded onto the main memory. In order to achieve that, all routines kept on disk in relocatable load format. It is useful when large amounts of code are needed to handle infrequently occurring cases. So for example, when you load some programs onto the main memory, you do not have to load all the exception modules onto the main memory, especially for those rarely happen exceptions. So they can be kept on the hard disk. So whenever the exceptional event happened, they can be dynamically loaded onto the main memory and handle those exceptions. And also, when using dynamic loading, so no special support from the operating system is required because they can be implemented by the program design. But the operating system can help with providing libraries to implement the dynamic loading. Now let's look at the last two concepts for memory management: static linking and dynamic linking. For static linking, system libraries and program code are combined by the loader into a very large binary program image. On the other hand, for the dynamic linking, the linking process will be postponed until execution time. In order to achieve dynamic linking, a small piece of code, which is called a stub, is used to locate the appropriate memory resident library routine. So when a library routine needs to be dynamically linked, the stub will be replaced by the addressed library routine. So surely the program needs to check whether the library routine is already on the program memory space. If not, the library routine will be loaded onto the program memory space first, then replace the stub to achieve the dynamic linking. So one thing I would like to mention is that when the library needs to be updated, the program does not need to be recompiled and relink with a dynamic linking. With this feature, it can make sure that the program can always use the updated libraries. So we call this feature as the shared libraries. Again, in summary, for dynamic linking, only the linking process is postponed until execution time, not the loading. So compared with the static linking, the dynamic linking can provide numbers of advantages, such as dynamic linking can save a lot of memory space because it only needs to load a small piece of code stub onto the memory space in terms of system libraries. And also the dynamic linking can always use updated system libraries.